assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So for question number 50, we have a nice little real-world example. I have tried to draw a pale facsimile of the picture in the book, but, I've done my best. The question wants us to use Ampere's law for part A to show that the magnetic field between the conductors of a coaxial cable is B mu I over 2 pi r. And for B, to show that the magnetic field is 0 outside the coaxial cable. So for A, that's what we'll do first, and we'll do it in blue. We look to Ampere's law, 20-9, which tells us that along a closed path, you have the sum of all your parallel fields, and then the delta length, the length unit, is equal to mu naught times the current that is enclosed. And for the path, we are going to choose a circle of radius r that is centered around the center wire here. And it's going to be greater than the radius of the inner wire. So something like this. And we have to choose something less than the radius of the outer band. And we will call the enclosed current these I's. So the blue I is the only thing inside the surface. So to continue, we have what we already wrote down. And if the wire is long enough, then the magnetic field is going to not have any transverse elements, so it's only going to be the parallel part of the field. Thus, we can just write our big B and then our delta L. But if you recall, the line unit, if we choose a circular path, is just 2 pi r, or rather it's 2 pi delta r, but if we do the integral or the sum over it, then this is equal to B times 2 pi r. I recommend you go back in the chapter to check up on that. You can either do it doing calculus or a infinitesimal sum. And put that aside, you rearrange that, and you get the near famous equation mu naught times the current over 2 pi r, which is what we're trying to find. Excellent. That worked out perfectly. Now for B, which we will use a devilish red, we are going to sort of use a similar argument, but the path is going to be a radius that is bigger than the braid. So we'll say the radius is, let's say the radius is way out here, just so I don't have to write over anything that I've already written. And this radius goes all the way around the wire. And again, the wire and braid are long and straight, so our parallel component is just the whole component. And let's write this out. So we have sum B delta L is equal to mu naught O I enclosed. However, I enclosed is I minus I, because we have an opposite direction, thus 0. So that's a tricky little thing, isn't it? We can go ahead and solve this immediately. Even if we do the 2 pi r, it's not necessary. we see that our magnetic field outside of this shielded wire is 0. And that's important actually, because that's how wires are shielded, by placing this, in this case, a cylindrical braid around the central wire.